This is the video of the Finck 2022 tutorial on purpose limitation and data minimization in data-driven systems. Hi, everyone. My name is Biega, and I'm a tenure-track faculty member at the Max Planck Institute for Security and Privacy, where I lead the Responsible Computing group. I'll be presenting this tutorial jointly with my colleague, Michèle Finck, who is a professor of law and artificial intelligence at the University of Tübingen. This tutorial is based on a recent paper published last year in Technology and Regulation. Please refer to the paper if you're interested in more details. In this video today, we're going to start with an introduction to the principles of purpose limitation and data minimization in GDPR. This is going to include an overview of the legal debates about the desirability of the principles, as well as an overview of the computational evidence that we have gathered that makes us think that data minimization could be implemented to a larger extent than it currently is in practice. We're then going to move on to cover purpose limitation in more detail. This is going to include the legal theory and components of purpose limitation. And those are specificity, explicitness, legitimacy, and compatible use. We're going to present some evidence of current implementations of purpose limitation by online platforms, as well as presenting recent computational approaches that define purpose for data collection in data-driven systems as service improvements. We're going to end this section with a discussion of computational challenges and open questions. We're then going to discuss the repurposing of data. This will include discussion of the means and conditions under which service providers can repurpose data, and this includes scientific research, statistical purposes, and consent. We're going to overview the associated practical challenges. A teaser here is that beyond the computational and legal challenges, our research has showed that for instance, the potential relationship between organizational structure of a company and their ability to repurpose data. We're then going to cover data minimization in more detail, and this will include the legal theory and the components of data minimization, that is relevance, adequacy, and necessity. We're going to discuss minimization of different types of data, including special categories of data, minimization of data quantity and quality. We're going to present the evidence for implementations by online platforms, as well as discussing computational approaches, challenges, and open questions. At this point, we will be ready to discuss the more general trade-offs in data protection that have been exemplified by our work on purpose limitation and data minimization. And finally, we're going to end this tutorial with an outlook that's going to include short-term recommendations for practitioners and the long-term research questions that we have identified. Okay, let's begin. All right, let's talk about a computational perspective on purpose limitation and data-driven systems. In our research for this work, we observed that service providers often state that user interaction data is collected to provide, improve, or personalize their services. We think that some of these purposes are not well grounded in current computational practice, as it is not immediately clear whether and which data is actually necessary to improve service results. Think about systems such as web search or recommendation. First of all, it is crucial to observe that in such systems, ongoing collection of user data is often not necessary to provide the results. User data is, in fact, used to improve the results. In web search, for example, a ranking of web pages can be computed by matching keyword queries to words appearing in web pages. And then, while processing a search query might be necessary to complete a given search transaction, it might not be necessary to store that query for future use once the search task is complete. In fact, we have seen personalization audit studies that have shown little search history-based personalization in major search engines. Beyond web search, in the domain of recommendations, results could be unpersonalized and based on external data. For instance, we could use sales statistics of cinema tickets as a popularity indicator to base movie recommendations on. We could even provide random recommendations. So personal user data might not be needed to provide a service, but it might be needed to improve the service. And service improvement could be considered an objective criterion for purpose formulation if it satisfied the three requirements for purpose: legitimacy, explicitness, and specificity. Determining whether improvement of a service is legitimate could be thought of as conditional on the legitimacy of the service itself. In most cases, we could think that improving a legitimate service might be considered legitimate as well. Explicitness, in the case of data-driven systems, could be enhanced by strategies previously proposed for other types of data, such as cookies. We could, for example, specify purposes in a machine-readable format. This is a strategy which, as argued by Koops, could force data controllers to reflect on their processing goals explicitly. Other approaches have proposed to improve explicitness of browsing cookie purposes by listing them in a structured table in a data processing policy. This strategy allows for quick identification of processing purposes by the data subjects. And solutions along these lines do appear viable for data collection purposes in data-driven systems as well. What about specificity? Our research has revealed that statements like improving user experience are unlikely to pass the specificity test. So how do we define data collection purposes in data-driven systems which are more specific? Von Grafenstein has argued that purpose standardization is something that could aid in increasing purpose specificity and legal certainty. Since then, everyone can be reassured that all data processing occurs under comparable conditions. In this spirit, for browsing cookies, researchers propose using ontologies to both standardize purpose descriptions and allow for reasoning about ontological relations between purposes, for example, subsumption. Purposes must be specifically defined, but at the same time, they should also be understandable by data subjects. And to achieve both goals, one might in practice use layered notices with more general statements providing an overall explanation for what the collected data is being used for, and then more detailed statements offering sufficient granularity. According to an interpretation that I mentioned earlier, some of the recent computational approaches to purpose limitation in data-driven systems interpret purpose as improvement in system performance. But there are many remaining questions as to what that might mean in practice and how to improve specificity under this interpretation. We could think about improving specificity along two dimensions. What is going to improve and how it's going to happen. Increasing specificity along the what dimension might entail defining which functionality in the system would explicitly be improved. For example, a layered description might generally indicate improvements in personalized search, and within that purpose, specify for which topics a data subject could expect improvements in their search results if certain types of queries are collected and retained. Increasing specificity along the how dimension might entail specifying how improvement will be quantified. For instance, the goal of a search engine might be to display relevant documents higher in the ranking results than they would be without the collected personal data. We could even go one step further because when we say improvement, that still sounds a bit ambiguous. and we might need a more computable definition in practice. Generally, it is reasonable to assume improvements would be quantified as differences in selected system performance metrics. Why this assumption? Performance evaluation is widely used to judge computational models and systems. We do this in scientific publications. We do this to measure progress in the field through public benchmarks. We do this to determine if updates to tech products should be shipped using techniques such as A/B testing. And practically, to form a quantitative basis of purpose using metrics, it remains to be determined which metrics to choose, how to obtain their values in practice, and which level to aggregate metric differences at. There are some challenges related to the selection of a metric. A metric would have to be selected from a set of metrics that typically guide system quality measurement jointly. The main reason for such complex evaluations is that different metrics capture different aspects of performance, and often none of these aspects are more important than others. And the selection will be hard, since individual metrics in a set will often disagree as to whether a change or additional data leads to service improvement or degradation. It is also important to acknowledge that metrics often serve as simpler quantifiable proxies for measurement targets. For instance, in systems such as search and recommendation, the goal might be to improve user satisfaction. And user satisfaction is typically approximated using simpler measurable concepts such as number of clicks. So it's important to recognize both the consequences and limits for using proxy metrics to determine which data should be collected and which data should not be collected. Okay, how do we get values of performance metrics in practice? They could be obtained using quantitative or qualitative evaluations, for example. In personalized search, the goal of a system might be to reduce the time necessary to find the desired information. And whether a system achieves this goal might be measured quantitatively using a metric such as the rate of search query rephrasing. Because when a user rephrases their query, that often means that the previous query has likely not yielded satisfying results. So the search engine did not do a good job. Or we could evaluate quantitatively through an in-person user experience interview or a survey. And finally, there might be multiple approaches to aggregating metric improvements. Among many possible options, a formal purpose definition might require that the collection of data improves the service on average for all users in the system, or that the collection of data improves the service for the individual for whom the data is collected. Because of all of these complexities, more detailed guidance will be necessary for practitioners to navigate all of these discussed design choices, since all the different choices might lead to different minimization outcomes.
As we have already mentioned, one of the biggest concerns about purpose limitation and data minimization is that limiting collection of data will inhibit future machine learning innovations. But there are certain conditions under which we can reuse or repurpose the data. Let's talk about the computational perspectives on those repurposing conditions. First of all, we can reuse data when two purposes are compatible. So when could we think of two purposes as compatible in data-driven systems? Under the purposes performance interpretation, and when performance is measured using well-defined metrics, one natural computational interpretation of compatible use is when metrics are positively correlated. Consider the following example. An online outdoor store originally collected personal data, such as product ratings, to improve the performance of personalized hiking gear recommendations. The store then expands its catalog to include hiking clothing. And it turns out that shopper preferences for certain categories of clothing and certain categories of gear are correlated. For example, this can be through the producer brand or price range or other features used for personalization. The data lawfully collected for the purpose of improving personalized gear recommendation will likely improve the clothing recommendations. So it could perhaps be argued that it can be used for the latter's purpose under compatible use. Practical implementations using this interpretation would still need to account for various challenges, including, for example, the existence of spurious correlations or the handling of implicit latent features in the algorithm. If we cannot reuse data under compatibility, there are still 3 avenues that could allow us to repurpose. The first avenue is using the data for scientific research. An interesting practical angle here is what can be considered scientific research in the context of commercial data-driven systems. Publicly funded and externally published work at academic institutions might perhaps uncontroversially be considered as research. But what constitutes research at private tech companies is perhaps less clear. Industrial research teams might do both internally and externally facing work, with internal research not meant for external publication, but rather for proprietary product development and innovation. To complicate matters further, various company organizational structures often make it impossible to distinguish who works on research and who works on products, despite official employee titles that might suggest a clear distinction. For example, we found documents that describe Google's organizational approach, where research scientists are often embedded in engineering teams. And as a result, many research scientists develop products, and many software engineers do externally facing research. We also found a description of the organization structure at Spotify, which is a company that does not follow traditional organizational hierarchies, and where employees with different backgrounds and titles are organized according to various functional dimensions, for example, system feature areas. The second avenue for repurposing data are statistical purposes. An interesting computational angle here is the question that has been a subject of debate in the machine learning and statistics communities. Is machine learning just a form of applied statistics? The statistical outputs considered here must not be personal data, but aggregate data. And moreover, those results cannot be used in support of measures or decisions regarding any particular natural person. It would seem uncontroversial that personalized services would have to be considered an individual measure. So to put it more concretely, the prediction of overall customer churn, for example, could be considered statistics, while the prediction of whether a given customer will leave and then targeting any services based on that result should probably be considered an individual measure. There's yet another distinction relevant in the context of this discussion about individual versus aggregate outputs, namely that machine learning pipelines produce aggregate and individual results at different processing stages. Many of the data-driven systems leverage large sets of user data to construct a model and then use such an aggregate model in conjunction with an individual's data to compute the individual results. For example, a search engine might train a non-personalized ranker that pre-selects web pages as a response to a query, and then use an individual's personal data to re-rank the web pages in the pre-selected set. In a scenario like this, the training of the aggregate model might be considered a form of statistical analysis, while applying the model in conjunction with an individual's data would not be a statistical result, but an individual result. One caveat to consider here is that there exist personalization algorithms that do not conform to this general scheme. For instance, in personalized recommendation models based on matrix factorization techniques, it might be that all individuals' data is used to train the model and produce personalized results at the same time. The third avenue allowing us to repurpose data is consent. The major challenge of acquiring informed consent for service improvements lies in explaining the value of improved results vis-a-vis the various costs of collecting different pieces of personal data. On the one hand, it is hard to expect the service providers to ask for such fine-grained consent when studies show that users have a limited understanding of the overall digital ecosystem, with some users not even aware that data such as search queries are stored and collected in the first place. On the other hand, existing studies on several related problems show that it is feasible to directly ask users for their privacy preferences when it comes to feature collection, for example, or indirectly estimate how much users value their data in the context of specific tasks such as disease prediction. There also exists other lines of work, including explainable AI or uncertainty and risk communication, which aim at communicating the outputs of computational systems to end users in an understandable way. While those two lines of work on privacy preferences and model output and risk communication are largely separate, it is possible to imagine combining both approaches to design informed consent solutions for service improvements in data-driven systems. An important technical consequence of consent is that data has to be erased once consent is withdrawn. And this can be particularly challenging in case this data was used to train machine learning models. We have only recently started developing techniques for efficient removal of such data without the need to retrain the models. And this continues to be an important problem if we want to be able to enforce the right to consent withdrawal without incurring high economic and environmental costs.
What got me as a computer scientist really interested in the topic of data minimization were the claims that data minimization is not really feasible anymore, that we live in a world of big data, that business models rely on the huge amounts of data we collect, and that machine learning models need all of this data to produce quality results. Yet, we managed to find empirical evidence in the CS computer science literature suggesting that this might not be universally true, that as we collect more data, we quickly reach diminishing returns in terms of model performance. For example, in this paper from 2008, this is a paper that focuses on personalized search, researchers looked at how the utility of a personalized search model changes as we include more and more features about users. And they observed this diminishing returns property here, to the extent that at some point it looks like new data does not add any value anymore, at least in terms of what this model can do. And we've seen similar evidence suggesting diminishing returns in other areas as well. Beyond personalized search, we've seen these types of effects in papers in the areas of natural language processing, computer vision, and in deep learning as a technique more generally. For example, Hessnes et al. In their paper on deep learning scaling show the existence of 3 different stages of model performance throughout data collection. They show the existence of this what's so-called the small data region, where the model has not learned the data distribution yet, and the model error remains high. Then as we collect more data, we enter what they call the power law region, where the collection of additional data improves model performance. So this is the stage where you can think of trading more data for improved model performance. And finally, there is the irreducible error region, where inclusion of additional data yields little to no return. And that this stage is could be thought of as particularly problematic from the perspective of data minimization. And we have observed similar performance stages in the context of recommender systems as well. In fact, we'll be presenting a paper showing this effect for recommender systems at the FACT conference this Thursday. Okay, so we have empirical evidence suggesting that models might not need all of the data we're collecting, but are there existing techniques that we could use to limit data? And the answer is, we'd argue also yes. We do have a lot of computational techniques that, in fact, can be seen as minimization techniques. Examples include, for example, outlier detection, which is a technique to remove noisy data. Another technique includes feature selection, where we remove certain data, for example, redundant data, before we train a machine learning model. Or active learning, where we selectively label data to feed to a machine learning model as we train it. These techniques have not been applied in the specific context of legal data minimization. They were developed towards different ends. Typically, we apply these techniques to improve or enhance the quality of models or reduce costs in terms of data annotation or data storage or compute time. So there are two lessons here. First, data minimization might lead to better models in certain cases, and it can even provide certain benefits for data processors as well, such as decreased storage costs or processing costs. And second, so even if we do have techniques that look promising, these techniques have not been applied in the context of data minimization or have not been researched in the context of data minimization. So they might require some work to be adopted toward legal compliance. Even beyond more sophisticated algorithmic techniques, one can easily think of simpler heuristics for retaining data. For example, we could systematically discard old data while retaining the new data that's coming in. We found papers that show the feasibility of this technique in the context of recommender systems. And generally, one might expect the strategy to perform well, especially in settings where user behavior and user characteristics and preferences change over time. And in cases like this, discarding old data might help systems keep user models and machine learning models up to date. We, in fact, have noticed that some online providers seem to be doing this. One of the recent changes in Google's data retention policy is an example. So what they now do is for new users, they propose for their new users that their web activity be automatically deleted after 3 or 18 months. And the fact that this is an official policy suggests that a heuristic like this might be an effective minimization strategy in industrial practice as well. Effects of limiting quantities of data are only one source of disagreement about the desirability of data minimization. Several studies have shown that it is also possible to reduce the quality of data without reducing its overall quantity. In one of our old papers, we demonstrated that it might be, for example, possible to achieve good levels of personalization for search and recommendations while randomly shuffling user data, data like search queries or product ratings. We would do this shuffling under certain accuracy constraints. And similar techniques have been adopted to show the feasibility of such data shuffling techniques in online communities as well. Effectively, approaches like this allow a system to retain the volume of data and preserve system accuracy while maintaining the quality, while minimizing the quality of aggregated user data profiles. We have also seen other architectures proposed in which a user's data resides on their local device, while only more crude aggregate data is shared with service providers on a need-to-know basis. And the feasibility of such algorithmic architectures have been demonstrated for personalized search. We have seen papers where, for example, what the authors propose is that users share only high-level topical categories describing their interests with the service provider instead of their specific search queries. And we have seen architectures proposed for recommender systems where a local tool advises the user whether to share their product ratings and product clicks with a recommender system provider based on a local privacy utility analysis. More generally, a local device distributed learning paradigm called federated learning is also an active area of research and can also be seen as a data minimization technique. Despite all of this promise of computational feasibility, data minimization can lead to unanticipated consequences for both the users and the service providers. Even if limiting quantities of data might lead to little accuracy loss at an aggregate level, as we have seen in a number of different papers across different application domains, studies have shown that data minimization might impact individual users or demographic groups to a different extent. This raises the question of what data minimization might mean in terms of fairness. Second, certain minimization techniques might lead to disparate data collection burden across different users. The paper that we'll be presenting at FACT this year shows this phenomenon for certain active feature acquisition techniques in the context of recommender systems. Minimization of sensitive attributes has furthermore been shown to hinder the capacity of service providers to audit fairness in personalized products. And finally, algorithms exhibit different levels of robustness to data minimization. This finding raises the question of how limitation obligations would impact different service providers and whether this impact would depend on how complex or state-of-the-art their algorithms are. Despite the existence of appropriate computational techniques and empirical evidence suggesting that it might be possible to limit data in data-driven systems to a much larger extent, minimization of, in particular, user-generated observational and behavioral data does not appear to be so widespread in practice. And we have been trying to understand the reasons why. The first reason we found is the lack of concrete operational implementational guidelines. We found a study of software developer approaches to data minimization that revealed that practitioner practices, day-to-day practices, differ both in terms of protocols and tools and even an understanding of what data minimization means and when it applies. We found some guidelines for implementing data minimization issued by the British and Norwegian data protection authorities. And these guidelines often focus either on more structured user attributes like location or gender, or discuss techniques, for example, techniques like learning curves, but offer guidelines at a very high level. So the guidelines would say, for example, inspect learning curves without saying how to actually translate it into practical mathematical definitions, algorithms, or decision rules. Beyond the lack of guidelines, we think there are a number of computational challenges related to implementation of data minimization in data-driven systems. The first and foremost challenge lies in determining whether and which data actually improves results. The state-of-the-art computing knowledge does not really provide off-the-shelf answers. The closest relevant line of work aims at quantifying the impact of individual data points in training sets on the accuracy of machine learning models using those sets. Such data points often correspond to individual persons and are composed of multiple pieces of information or features of those people. And to the best of our knowledge, methods that would quantify which individual pieces of data about an individual data subject are necessary to personalize different services or quantify these improvements are missing. What is more, determining whether a piece of personal data should be minimized out because it won't contribute to the positive improvements in terms of the model performance will be a form of prediction about the future system performance. And these predictions can reasonably be expected to be inaccurate. And there's the question of what level of inaccuracy would be acceptable for this form of data minimization to be deemed practically viable. Beyond the prediction accuracy, the determination of how much and what personal data is to be kept for a given performance purpose depends on a number of factors. And those factors include the prediction method itself, the underlying service algorithm, existing user data of a particular individual for whom we want to minimize data, but also the entirety of other data about other users that is at the disposal of the service provider. And of these factors, two merit special attention. First, data minimization outcomes will largely depend on the underlying algorithm. Advanced systems employing complex models that need to learn many parameters might require more data to function properly. So, by developing and implementing state-of-the-art solutions, service providers might be able to collect more personal data. On the other hand, we also saw papers that suggested that infusing vanilla models with domain-specific knowledge might allow better model performance with smaller data sets. And so less need for data collection. These observations lead us to a number of questions of economic nature. If less data can be collected with custom models, would companies who can afford an internal research unit be able to minimize data better? Or if bigger models grant a data processor the right to collect more data, will companies who can afford the often very costly infrastructure necessary to operate these models, would these companies be allowed to collect disproportionately more data? The second factor worth worth highlighting is the complex balance and interdependence of the data of different users and the system performance for those users. It might be tempting to think of the system as static when considering which pieces of an individual's personal data to minimize out. But in practice, the data that is minimized out for a given individual might constitute the system training data for other individuals. So minimization of data for a single user will also influence the performance of the system for other users. And we really need a global systemic approach that at the same time works for each individual separately. And last but not least, setting aside the processor's purposes and taking a user's perspective, it is important to recognize that different people might have different personal purposes when using a service and generating some data. For instance, a user might generate a movie rating purely to give the provider the information needed for personalized movie recommendations, in which case the performance-based minimization might appear appropriate. But we might have another user who generates movie ratings for personal archiving purposes, to store a log of movies they have seen. In this case, the storage of all personal ratings appears appropriate. And so it might be necessary to not only model the purpose of the data collection by the service provider, but also the purpose of data generation by the user. But this is by no means easy. And the need to model user personal purposes further branches into two challenges. First, it is rather difficult to infer user intent from their behavior. Recognizing people's search intents from text queries, for example, continues to be an active research problem in information retrieval. And second, users might engage with technology in originally unanticipated ways. Some people, for example, use email, a technology developed originally as a communication tool, as a task management and archiving system. If we're not able to model intents and personal purposes correctly, such inaccurate detection might lead to both under and over minimization of data, depending on the context. Hopefully, this tutorial has given you an overview of the current state of purpose limitation and data minimization in data-driven systems. What could practitioners be doing now, and what could we do next? It's heartening to see that there has been a growing interest in this topic in the computational community. If you're interested, take a look at some of these papers. In our paper from SIGIR 2020, we proposed a performance-based interpretation of purpose limitation and what it would mean to minimize data according to this interpretation, both globally at a model level and at the level of individual users. Clavel et al. Explored tensions between data minimization and the feasibility of bias audits. Rastegarpana proposed a method for auditing feature-based data minimization. Goldstein et al. Proposed a method for feature-based data minimization using anonymization techniques. And Shanmugam et al., this is our paper, which will be presented at the FACT conference, proposes a machine learning approach to automating data minimization during data collection. Even though the implementation of purpose limitation and data minimization in the context of data-driven systems requires more research, practitioners might consider implementing a range of existing solutions and best practices that contribute towards data minimization. The first organizational best practice is for employers and employees to create and cultivate a mindset of reflecting on the purposes of data they collect and of continuously reevaluating which data should be collected and when it should be deleted. To quantify the importance of different pieces of data, practitioners can use off-the-shelf solutions for machine learning models, including feature selection, data influence estimation, or data evaluation. At the data collection time, techniques such as active learning would allow data processors to prioritize which data is the most important for a model's quality. Data can also be minimized through simpler heuristics, such as selection of representative random samples, selection of data specifying certain domain-specific quality criteria, or retaining only the most recent data. For instance, in the context of product recommendations, a data controller might retain only the most recent product ratings generated by a user while discarding their old product ratings. You could retain only the ratings for the most popular products or only the ratings with the highest or lowest values. And finally, minimization should be employed not only at the data collection time, but also continually reapplied throughout a system's lifecycle to every existing data store. To be technically implementable in the context of data-driven systems, purpose limitation and data minimization will likely need to follow a similar research trajectory as that of work in algorithmic fairness. As demonstrated throughout this tutorial, we need mathematical interpretations of the principles. We need decision rules for deciding which pieces of data are necessary and which should be discarded. We need machine learning models that could automate compliance, as well as quantitative data analysis for understanding how the implementation of those principles might influence the quality and functioning of online ecosystems. We need standardization of data processing purposes to ensure their specificity, as well as an understanding of how different purposes relate to each other to reason about their compatibility. We lack an in-depth understanding of what value people associate with different types of data in different contexts. We should, moreover, design appropriate transparent mechanisms for collecting informed data processing consent and technical means of removing data from existing models and infrastructures once a purpose has been fulfilled or once a user withdraws their consent. We need auditing methods that could establish compliance with the purpose limitation and data minimization requirements. And finally, we need to establish normatively, legally, and computationally how to balance data minimization with other GDPR requirements such as fairness or accuracy, which have been shown in some of the computational work I showed you the references to that could be at odds with the minimization principle. As the work on algorithmic fairness has previously exemplified, it is difficult to bridge terminological and substantive gaps between disciplines. We may wonder whether and how legal principles, and particularly broad principles like data minimization, purposefully kept vague to enable contextual interpretation, could be translated into algorithms and code. Without doubt, this is a question at the core of the fact community that requires more engagement from multiple disciplines. And we're excited and hopeful to see more work in this area in the future. Thank you.